Imagine a car that can leave your driveway without starting its gasoline engine, drive silently through the city using nothing but electricity, and then when the battery runs low, switch seamlessly to gasoline and keep going. No range anxiety. No choosing between an EV and a conventional car. That's the basic idea behind the plug-in hybrid electric vehicle, or PHEV. But what actually happens underneath the car? How do two completely different power systems work together, and why would anyone put both an electric motor and a combustion engine into the same vehicle? Let's take a look inside. At first glance, a PHEV looks like an ordinary car. There's a familiar body, 4 wheels, a fuel tank, and an engine. But underneath there's another entire propulsion system. A large high-voltage battery stores electrical energy. An electric motor converts that electrical energy into motion. Power electronics control exactly how much electricity reaches the motor, and an onboard charger allows the battery to receive energy from an external power source. So instead of having one way to move the car, a PHEV essentially has two. Gasoline can provide the energy, electricity can provide the energy, and the vehicle's control system decides how to combine them. Let's start with the battery. Unlike the small battery found in a conventional hybrid, a PHEV carries a much larger traction battery. That extra capacity is what allows the vehicle to travel a meaningful distance using electricity alone. Depending on the vehicle, that can be roughly 15 to more than 60 miles. For many drivers, that completely changes the daily driving experience. Imagine leaving home in the morning with a fully charged battery. You accelerate away from the driveway. Instead of the familiar sound and vibration of an engine, the electric motor immediately starts delivering torque to the wheels. Electric motors are extremely good at producing strong torque from very low speeds. That's why an electrified car can feel surprisingly quick and smooth when you press the accelerator, and during short city trips, the gasoline engine may barely need to participate at all. But where does that electricity come from? This is where the charge port enters the story. Plug the vehicle into a wall outlet or charging equipment, and electricity flows into the car. But the battery can't simply accept household AC electricity directly. The onboard charger manages that incoming power and converts it into the form required to charge the high-voltage battery. The vehicle continuously monitors things like voltage, current, temperature, and battery state of charge. Once charging is complete, the system stops drawing power as needed. Now imagine you're driving again. Electricity leaves the traction battery and travels through the vehicle's power electronics. The power electronics controller acts like the traffic manager of the electrical system. It controls how much electrical energy reaches the motor. More power means more motor torque. Less power means less torque, and that gives the vehicle precise control over acceleration. The motor then converts electrical energy into mechanical rotation. That rotation ultimately reaches the wheels and pushes the vehicle forward. But here's where things get really interesting. The car doesn't only recover energy when it's plugged in, it can also recover energy while you're driving. Every time a conventional car slows down, much of its kinetic energy is converted into heat through the brakes. That energy is essentially lost. A PHEV can do something smarter. During certain braking and deceleration conditions, the electric motor can work in reverse. Instead of consuming electricity to turn the wheels, the rotating wheels drive the motor. The motor now behaves like a generator. Mechanical energy becomes electrical energy, and that electricity flows back into the battery. This is called regenerative braking, so the car can capture some energy that would otherwise disappear as heat. But what happens when the battery gets low? This is where the second half of the PHEV system takes over. The internal combustion engine can start automatically. Fuel is injected into the engine, mixed with air, and ignited. The engine produces mechanical power, and depending on the vehicle's architecture, that power can reach the wheels directly, help the electric system, or generate electricity. And this brings us to one of the biggest differences between PHEVs. There isn't just one universal way to combine the engine and motor. Some systems use a parallel configuration. In this arrangement, both the engine and electric motor can contribute mechanical power to the wheels. Think of it as two power sources working together. At low speeds, electric power can take much of the workload. During stronger acceleration, the engine can join in. And at higher speeds, the system can select the combination that makes the most sense for efficiency and performance. Other systems take a different approach. A series-style configuration can use the electric motor as the primary source of wheel propulsion. The combustion engine can then operate more like an onboard power station, generating electricity for the electric drive system. Some vehicles can even combine different operating strategies depending on speed and battery condition. The result is a highly flexible powertrain. But there's an important catch. A PHEV only delivers its biggest electric advantage if you actually charge it. Imagine buying a plug-in hybrid and never plugging it in. The vehicle can still operate using its combustion engine and hybrid system, but you're carrying around a relatively large battery without taking full advantage of it. Charge the vehicle regularly, however, and the story changes. A short daily commute can potentially be completed mostly or entirely using electricity. Then the gasoline engine becomes the backup for longer journeys. That gives the PHEV a unique position between traditional hybrids and fully electric vehicles. A conventional hybrid doesn't normally depend on external charging. A battery electric vehicle relies entirely on its battery and electric motor. A plug-in hybrid sits between those worlds. It can behave like an electric car for shorter trips, and like a gasoline-powered vehicle when longer-distance flexibility matters. Of course, that flexibility comes with complexity. You've got a battery, an electric motor, power electronics, a charger, a combustion engine, a fuel system, a transmission, cooling systems, exhaust components, and a sophisticated control system coordinating all of them. There's even a separate low-voltage auxiliary battery that powers many of the vehicle's conventional electrical functions. The DC/DC converter helps bridge the gap between the high-voltage traction system and the vehicle's lower-voltage electrical systems. And the thermal management system keeps critical components within their required temperature ranges. All of these systems have to work together without the driver needing to think about any of it. And that's perhaps the most impressive part. You press the accelerator, and the vehicle decides how to respond. You lift off the accelerator, and it can decide whether to coast, regenerate energy, or use braking. The battery gets low, and the combustion engine can enter the equation. You plug the car in overnight, and by morning, the electrical side is ready for another trip. Two propulsion technologies, one vehicle, one control system coordinating the entire operation. That's the fundamental idea behind the plug-in hybrid. It's not simply a gasoline car with a bigger battery, and it's not quite an electric car with a backup engine. It's a carefully engineered combination of both worlds. And depending on how and where you drive, that combination can turn a single vehicle into something remarkably versatile. Electric power for the everyday drive, gasoline power when the journey gets longer, and regenerative braking and external charging helping put energy back into the system along the way.